Aloha! Thelma Parker Memorial Public Library of the Hawaii State Public Library System welcomes all of you joining us today. To promote STEM learning in our communities, Thelma Parker was selected as the only library in the state of Hawaii to participate in NASA at My Library program. We are delighted to welcome home E Komo Mai, Dr. Jessie Tarnis, for today's program. Jessie is a Parker School alumnus and recently earned his PhD in planetary science from Brown University. While growing up here in Waimea, Jessie often visited Thelma Parker Library, and now, ta-da, he is a member of the science team for the Perseverance Mars Rover. And now, Dr. Jessie Tarnis.
All right. Thank you so much, Pamela. And it's awesome to be talking with you all. I really appreciate the opportunity. And, you know, it's amazing. I remember in elementary school, especially when I was going to Hawaii Montessori school, every Thursday we would walk from the school about maybe a mile to Thelma Parker and get to read all the books there, listen to books being read to us about a variety of interesting things, and work on our reading and writing. And it's at my parents' house in Waimea. I still have my original Thelma Parker Memorial Library card that I was able to get after being able to write my name when I was in kindergarten. My handwriting has slightly improved since then, but it's a cool memento, and I think it's still valid. I could still go check out a book if I wanted to, so that's great. Thank you all for coming today. I really appreciate you being here, and I'm super excited to be able to talk with you all. This talk will be about the search for alien life and a home on Mars. And this really centers around this most recent Mars rover that's landed, the Perseverance rover, that I'm fortunate to be able to work as a science team member on. So I am a NASA postdoctoral fellow at the Jet Propulsion Laboratory, JPL, which is where they've built most of the robotic spacecraft that have gone out into the solar system since the decades ago. Everything from the Voyager spacecraft that traveled out beyond our solar system, beyond the heliopause into interstellar space, to all of the past Mars rovers, to some missions that orbit Earth to study our home planet. So let's get into it. So I'll start with this image. This is a view of an astronaut climbing out on the exterior of the International Space Station with a camera strapped to their helmet here. This is a huge satellite where astronauts have been living for decades now. So ever since this International Space Station was first put up and began to be assembled from different parts in space from different countries, there has always been a human presence in space for all those decades. Now, this is a huge satellite with solar panels that are about the size of a football field. So when you see it flying overhead, you can tell it's the International Space Station just from how bright it is. Often, if you'll look up, even if you haven't seen a satellite before, you can look up at the sky more now, and you'll see these things that look like stars traveling across the sky. And they're often not very bright. They're like a faint star just traveling across the sky. That's a satellite. This International Space Station is so big that it looks like a bright star or a planet traveling across the night sky. And this is really the key first step to getting humans to permanently inhabit the moon, Mars, and other planetary objects. So we've had humans in space for decades, and the journey's just beginning. Now, a lot of this talk is going to be about Mars, and Earth and Mars are very different planets. On Earth, we have, as you're all very familiar with as inhabitants of Earth, a cycle of water and air and clouds and rain, with plants everywhere that feed into a biosphere of interacting organisms, be it humans, plants, or animals, where energy is constantly recycled back into the environment, largely driven by photosynthesis and the presence of liquid water. Now on Mars, the conditions are very, very different and much harder for life to exist. On the surface, it's in fact impossible for plant or animal life to exist, and humans can only exist there by using technology to allow us to survive these harsh conditions. So on Mars, the atmospheric density is only about 2% of the atmospheric density on Earth. So it's much closer to being kind of in the vacuum of space where there's no air. than it is to being in the nice pressurized environment of Earth with oxygen. The atmosphere of Mars is mostly carbon dioxide, which humans also can't breathe. And conditions on the surface are generally extremely cold. It can get to above freezing temperatures in the summer, but the pressure is still too low for water to be a stable phase in liquid form. There's also a lot of radiation hitting the surface because while Earth has this thing called a magnetic field that sort of shields it from all this radiation coming from the sun, as well as an ozone atmospheric layer that shields some radiation, Mars doesn't have any of that. There's strong radiation on the surface. It's a much more difficult place to live. But we're going to talk about later in this talk a time when Mars might have been much more Earth-like and how we can explore that ancient environment by the story that's told in the rocks that are on the surface of Mars today, and how by using technology, humans can eventually be able to live on this planet and permanently inhabit it. So Mars is very far away from Earth. It's if you think about the distance between Earth and the sun, Mars is about half that distance away from Earth. So about half as far as Earth is from the sun. And we can see Mars in the night sky. So here's a picture of it labeled here. It's often got a reddish color to it. And we can also see Earth from Mars. So this is a picture that was taken by the Curiosity rover in Gale Crater. And you can see that little dot there from Mars. That is Earth. That is every single human, animal, plant that's ever existed in our solar system. I suppose there could have potentially been microorganisms elsewhere in the solar system, but everything that's ever existed in the Earth system has existed in that small dot. And the journey of traveling from Earth to Mars, whether it's a robotic spacecraft going or humans going, is really going between two very, very small points covered by a long distance in space. And I think that actually the most similar experience that humans have had during the course of history before we were inhabiting space to this journey, is traveling between small islands across vast expanses of the Pacific Ocean for the Polynesian voyagers and Hawaiian voyagers. It's a similar set of problems to accomplish this task, where you have to go from one extremely small piece of land to another extremely small piece of land with a vast expanse of something you can't stop on, in this case, ocean, in between. And in the case of Mars and Earth, those extremely relatively small pieces of land are whole planets, but with the huge distance of space in between them, they're actually relatively quite small, and you have to hit your target precisely here. Similarly, the Polynesian Hawaiian voyagers used celestial navigation to orient themselves in space as they were traveling between their origin point and their final target point, and that allowed them to precisely get to where they wanted to go. Spacecraft, as they fly between planets, also use a similar technique to this through something called star trackers. So these are cameras on the outside of the cruise stage of the spacecraft that holds, in this case, a Mars rover inside of it. And it images stars in specific patterns to try and determine what its orientation is in space. So there's a lot of parallels here to the culture that is the root of the culture that we've all grown up in Hawaii, and space exploration. So this is the star of our story here, the Perseverance Mars rover. And this is an image that was taken of it as it had just been assembled in the JPL high bay, which is where a lot of these robotic spacecraft that have traveled out into the solar system have been assembled for decades. And so take a look at these wheels here. These are some nice wheels, new and improved from the other Mars rover. This rover is then packed up, compressed into its travel mode, and put into something here that is called a back shell. So those wheels I was pointing out before are these wheels here that are now covered in protective material. So it's folded up and inserted into this back shell that is then placed on top of this thing called a cruise stage that will take this back shell in the rover through space to Mars. And now in the next picture I'll show you, this area of the back shell that contains the rover will be capped by a heat shield that will protect the rover upon its entry into the atmosphere of Mars. So there it is, the same picture, but now that heat shield cap is on there. So we'll see in a video later in this presentation how this heat shield protects the rover as it enters the atmosphere and then eventually breaks away to crash land on the surface of Mars during the landing process. Eventually, that whole package that contains the rover is put together in to this object here that is actually going to form the top of the rocket. So this kind of cap that the rover is going to be put in is what's placed on top of the rocket, and then the rest of the rocket is all propellant that will be able to launch this thing off the surface of Earth to Mars. That rocket cap is then transported to the rocket that contains all that propellant, all that fuel. It's like the gasoline that your parents or you put into your car, but the material that provides that fuel source isn't gasoline. It's a different, much more high energy material that can allow for this kind of rocket transport off of the surface of Earth. And on July 30th, 2020, this rover was launched on a rocket off of the surface of Earth and began its journey to Mars. Now this date, July 30th, 2020, was selected for a very specific reason. This wasn't a randomly chosen date. This was during this sort of 2-month window when Earth and Mars are as close to each other as they ever get. And if in fact the engineers who were building this rover missed this launch window, which was a very real possibility at certain points, especially due to the pandemic setting in, making work, because these engineers, they work with their hands, they work on teams, they work together, and there was a very real possibility of missing this deadline. And if that had happened, we would have had to wait 26 months to launch again. Now let me explain to you why that is. So here is a visualization of our inner solar system, so going from the sun all the way out to Mars. Things are not to scale here. So for example, this blue here is Earth's orbital path around the sun, the ellipse that's pretty much circular, in which the Earth travels around the sun. And then the red here is the ellipse in which Mars travels around the sun. The actual planets Earth and Mars are much smaller than the lines that form these circles here. So I exaggerated the sizes here so that you can see more of what's going on. So this is the position that Earth and Mars were in when the Mars 2020 rover, the Perseverance rover, I might use those names interchangeably, Mars 2020 rover and Perseverance rover. This is the position the planets were in when it was launched on July 30th, 2020. And now you can imagine that this is about as close as these planets ever get. Everything's rotating counterclockwise in this system here. So you can imagine that if Earth, for instance, was over on this side of the circle and Mars was on this side of the circle, the actual distance between them would be much larger than it is when they happen to get this close. And they happen to get this close every 26 months because the Earth, since it's closer to the sun, happens to be traveling faster around its circle than Mars does. It only takes Earth 365 days, 1 year, to travel all the way around the sun, whereas on Mars it's a little more than 680 days. So it's almost twice as long that Mars takes to complete that orbit. So Earth is constantly catching up to it every 26 months, providing this launch window. So it wasn't just NASA that launched a rover to Mars during this 2-month period. China also launched a rover to Mars, and the United Arab Emirates also launched an atmospheric spacecraft that'll study the atmosphere of Mars during this period of time. Okay, so now let's watch as the rover advances on its journey from Earth to Mars. So this is a couple months later, as the rover's traveling from Earth to Mars. You can see that everything is moving in this direction, including the rover. So the rover has all that speed that it had just from being on Earth, the speed that you and I are experiencing right now just from existing on Earth. But it's getting kind of thrown by the rocket from Earth to Mars. And it continues to travel on this trajectory with the planets, but also crossing that gap, shooting the gap in between the planets. So this is sort of like if you and your friend were running next to each other in a field, and one of you were to throw the Frisbee to another, that person could continue running and then catch it because the Frisbee has the speed of both your running, but also of the throw that you made to get that Frisbee to your friend. So sort of conceptualize that that's what's happening here. And the Mars rover is the Frisbee, and Earth and Mars are you and your friend. So it continues to travel from Earth to Mars here, and then finally starts getting closer to Mars. And when the planets were in this configuration on February 18th of 2021, so a couple months ago, this is when the rover actually reached Mars. So you can see it's about 6 months later. And so Earth has gone from being on this side of the sun to being on the opposite side of the sun, because about half a year has passed. Whereas Mars has gone from being about here to being about a quarter of the way around the sun, because only about a quarter of its year has passed. And so this is, again, very, very difficult problem of getting from one small piece of land in the solar system to another, traveling through a vast expanse of space, something similar to what ancient Polynesian voyagers and Hawaiians were very skilled at doing. And this is how we get spacecraft to other planets. Now, the most difficult part of getting to Mars, if you want to get to the surface, is making landfall. It's like trying to get a 6-person outrigger canoe onto shore when there's like 50-foot waves and everything's going crazy. This is a difficult task. And I'll show you a video later where we actually captured it happening for the first time. So this is an image of the rover itself being lowered to the ground by this spacecraft here, which is called Sky Crane. So even though you can't see it, there's rocket jets coming out of these thrusters here that are steering this spacecraft and keeping it up so it can lower the rover to the ground. So we'll see more of this later. The way that making landfall on Mars works is the engineers at the Jet Propulsion Laboratory, who have gotten better and better at this with every single time they've attempted a landing on Mars, give an ellipse. So this is the ellipse here. And they say, okay, we can guarantee with 99% confidence that we can land somewhere in this ellipse. So this ellipse is 8 kilometers wide by 7 kilometers tall. And all of these green and black points here are points where we can tell it's safe for the rover to land in. We don't want to land in an area like over here where there's a bunch of dunes, because the rover could get stuck and not be able to traverse out of those dunes, and that would be mission failure. We don't want to land along this cliff face here, because the rover could be damaged and also definitely get stuck, which would be mission failure. And we don't want to land on a lot of these areas here that are covered with boulders, because the rover could land in some weird orientation and not be able to move or be damaged. So we have to hit, or the engineers at JPL had to figure out how to hit one of these points during the landing sequence. And that's very hard to do. The original landing ellipses for Mars rovers in, say, like 1994, when I was born with Pathfinder, were more than 10 times the size of this thing. Just huge. And so that really cut down on the available areas to land, because you just couldn't guarantee safe landing on other areas. So with every single rover or lander that's come to Mars, the engineers have gotten progressively better and better at getting this landing system working, until finally we're able to land in this wonderful place called Jezero Crater that I'll talk about in a little bit. And to show you what the aftermath of the landing is before we watch the video, these are all the different pieces that play a role in the landing process itself that have all either crash landed or gently landed, in the case of the rover, on the surface of Mars after the event. So here's the heat shield, which we saw when it was capping the rover back at JPL on Earth. Here's the parachute and back shell. So we saw that back shell, again, being that thing that the rover was folded up and then inserted into. And this is the descent stage. So this is what we saw just a few slides ago, dangling above the rover with its rockets and lowering it down to the surface. And finally, here's Perseverance, where it landed safely on the surface. And we can see through orbiters that are orbiting Mars hundreds of kilometers in the sky around the planet, taking high resolution pictures. We can actually see all of these individual components on top of the Martian surface, including the rover, which is safely landed here. And this is the first image that we got upon landing. So now I'm going to show you a video, this is a historic video, and perhaps the coolest thing I've ever seen. that was captured for the first time, this event of the rover landing on the surface. So this room here that we're looking at is mission control, where they were controlling this whole entry, descent, and landing EDL sequence to get the rover from the top of the atmosphere to the surface of Mars. Now, keep in mind, when this rover first hits the top of the atmosphere, it's going at a speed of about 3 miles per second. So take a second to think about that. You've probably gone 3 miles either by walking somewhere, maybe on a hike, maybe to your friend's house, or biking 3 miles somewhere, or riding in your parents' car or driving somewhere else. Maybe your auntie and uncle's house is 3 miles away. It probably takes you a lot longer than a second to get there. And in a car, you can actually be traveling pretty fast. So think about how fast this spacecraft has to be going to get to Mars at a speed of 3 miles per second. And now this team needs to figure out how to slow down the spacecraft from that very fast speed to a relatively slow speed of 0 miles per hour when it finally touches down gently on the spacecraft. So I'll show you this video here and narrate it as we go through.
We are starting the straighten up and fly right maneuver, where the spacecraft will jettison the entry balance masses in preparation for parachute deploy and to roll over to give the radar a better look at the ground.
Applicant indicates parachute deploy.
All right. So just pause and tell you what's happening here. So this is the parachute that is going to slow the rover down as it enters the atmosphere at 3 miles per second. The heat shield part of it, which you aren't able to get a video of just because of the high energy nature of this event, basically came through the atmosphere like a shooting star. So there was fire and plasma, or plasma that looked like fire, emanating from the front of that heat shield just from the friction of that spacecraft traveling so fast through the atmosphere and slowing down. So it's like the brakes on your bike or your car. But you know, sometimes if you brake really hard on your bike or your car, you can sort of smell the brakes. It smells hot. That's from the heat of the friction of the brakes against the wheel. And so the heat shield is sort of like that, but the heat is from the heat shield going against the air on Mars so fast that it forms something that looks like a shooting star. That's the same thing that forms shooting stars on Earth. And so after that stage, after it had slowed down enough, even though it's still traveling much faster than the speed of sound here, they deployed this parachute, which shoots out about 100 feet behind the rover here. And it's about 70 feet wide to start slowing it down more and try and get it going slower than the speed of sound. So that's what's going to happen here.
Navigation has confirmed that the parachute has deployed, and we are seeing significant deceleration in the velocity. Our current velocity is 440 meters per second at an altitude of about 12 kilometers from the surface of Mars.
All right, so this is the event where the heat shield, which we saw capping the rover and that protected it as it was coming in really fast through the atmosphere, this heat shield is now separating and going to fly off and crash land on the surface so that the rover itself can start taking radar data and images of the descent to try and stick the landing in the right location. So you're going to hear them say heat shield sep, which means that heat shield is separated. It's going to fly, it's going to crash land on Mars away from the spacecraft as Perseverance tries to figure out exactly where the safe place is to land based on how it's coming into the surface here.
Heat shield set.
Perseverance is now slowed to subsonic speeds, and the heat shield has been separated. This allows both the radar and the cameras to get their first look at the surface. Current velocity is 145 meters per second at an altitude of about 9.5 kilometers above the surface.
Wow. This video, I've watched this at least 50 times, and it still blows my mind every time. So you can watch it 100 times and see all the detail you can pick out.
Net filter converge. Velocity solution 3.3 meters per second. Altitude 7.4 kilometers.
Now has radar lock on the ground. Current velocity is about 100 meters per second, 6.6 kilometers above the surface of Mars.
So you can see that it's kind of moving back and forth.
Continuing to descend on the parachute. We are coming up on the initialization of terrain relative navigation, and subsequently the priming of the landing engines. Our current velocity is about 90 meters per second at an altitude of 4.2 kilometers.
So you see how the camera's sort of shaking around back and forth like that? That's the actual wind on Mars in the air from the speed of the spacecraft entering, with the parachute hanging behind it, sort of moving it back and forth as it's coming in and slowing down. And what they said earlier, that they have radar lock on the surface and they're about to engage terrain relative navigation. This is the technology that allows the rover to land in such a small area, because all of this is being done autonomously. It takes minutes, several minutes for light or radio waves, any type of communication to travel from Mars to Earth. So all of this has to happen by itself via a computer that's uploaded into the rover's software brain before it gets to the planet. So by the time mission control and we on Earth receive all this information of how the landing's going, it already happened several minutes ago. And so it has been decided, it has happened, whether the rover has crashed into the surface or landed safely there. So the robot is doing all of this by itself due to the awesome work of hundreds and hundreds of engineers who have built this system. So now what you're going to hear is they'll say back shell SEP. That means that back shell with the parachute on it is going to separate away from the rover, and that spacecraft we saw before with the rocket thrusters on it, which is called Sky Crane, is going to start flying the rover to a safe landing location with those rockets. So you'll see, after they say back shell SEP, you'll see the image kind of move to the side like this. And that's the Sky Crane literally flying the rover to the correct location for it to safely be lowered down onto the surface. So here we go.
LVS valid.
We have confirmation that the lander vision system has produced a valid solution and part of terrain relative navigation.
Priming. TBA is nominal.
We have priming of the landing engines.
Here we go. Back shell SEP coming up.
Back shell SEP.
Current velocity is 83 meters per second at about 2.6 kilometers from the surface of Mars. We have confirmation that the back shell has separated. We are currently performing the divert maneuver. Current velocity is about 75 meters per second at an altitude of about a kilometer off the surface of Mars.
TRN safety Bravo.
All right,
we have
flying in.
Completed our terrain relative navigation. Current speed is about 30 meters per second, altitude of about 300 meters off the surface of Mars. We have started.
Here we go. So what you're about to see now is, as it's coming into the surface of Mars, still coming in pretty fast at like 30 meters per second from being up at 300 meters above the surface. It's now going to come down straight, but slow down with those rockets so that it can get to basically standing still, 0 miles per hour, and then lower that rover down on tethers onto the surface. And so you'll see as it's coming in closer and starting to slow itself down with the rockets here, the dust will start blowing up everywhere, kicked up by the rocket.
Started our constant velocity accordion, which means we are conducting the Sky Crane, about to conduct the Sky Crane maneuver.
There we go. So they're about to lower the rover to the ground. So as this is happening, this picture is being taken by this rover here. So it's looking up. And then this picture of the rover is being taken by Sky Crane here, looking down. And so Sky Crane is hovering above the surface with its thrusters, blowing up all this dust and lowering the rover down to the surface now. Once the rover is safely there on the surface and it senses that it's contacted the surface at low velocity, those tethers connecting these spacecraft, these four here, will be severed, and then Sky Crane you'll see it fly away, and then it'll crash land several hundred meters away from the rover to keep the rover safe there. So that's what you'll watch right now. And then once that happens and Sky Crane flies away, listen for the words touchdown confirmed, because since we didn't have these videos when the rover landed, all we had was the audio you've been hearing. These videos came back days later when we were finally able to get them. So what we were all listening for as we watched this were those words touchdown confirmed, which means that the rover got there safely on the surface.
Sky Crane maneuver has started, about 20 meters off the surface.
We're getting signals from MRO.
Tango Delta.
Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the signs of past life.
All right, so you saw how excited everyone was during that landing when the words "touchdown confirmed" were finally said. So I was in a virtual meeting space with the rest of the science team members during this time, about 200 of us, also watching this. Everyone was staring intently at their screens while we were all together in virtual space watching, and we all had similar reactions when we heard "touchdown confirmed." You jump up. You triumphantly kind of shout and yell and get excited, and you can see that they also are celebrating with each other. They're celebrating being there as a team that has successfully done this, and that's one key thing I'd ask you to take away from this talk is that doing these types of missions to other planetary objects requires a team. Not a single person cannot do this by themselves. This mission required almost 1,000 people, maybe over 1,000 people, to put everything together to make something that could seem so impossible, like landing on Mars, happen smoothly and happen well. And that's the same that goes for pretty much anything in life. It's the same that would go from making a voyage from Polynesia to Hawaii. You're not going to do that on your own. Eventually, you're going to need to go to sleep, or eventually you'll be doing a task that is taking up all of your attention while another task needs to be done. It takes teams and teamwork and being a good teammate to make these sort of amazing things happen. And I think that NASA and JPL is really demonstrative of that. And this whole step of getting to Mars is proof of it. Okay, so now to get back to the slides here. This is the first image that we got back in a bit higher resolution once we touched down on Jezero Crater itself. So now, as you heard in the end of that video where they said Perseverance is touchdown, ready to start seeking signs of ancient life. We'll talk about what they mean by that now. So on the left, we have a picture of modern Mars. So this is Mars today, an actual picture that was taken of Mars today. On the right, we have an artist's conception of what Mars might have looked like more than 3 billion years ago, when its environment on the surface might have been a lot more like Earth, where you had lakes forming on the surface and rivers of liquid water flowing across the surface here. So what we're going to look at Jezero Crater is to look for evidence that's held in the rocks there of this more ancient time of Mars when the surface could have been habitable. And here's a little video graphic showing what it would kind of have been like for Mars to have gone from being this kind of wet planet with water on its surface, forming lakes and rivers, to drying out into the cold red object that we see today. So we're looking for the story that's told in the rocks of Jezero Crater for what that ancient watery environment would have been like and if life could have been supported there. So this is a map of topography on Mars. The white and reds are high elevations like Mauna Loa, Mauna Kea. The blue are the lower elevations. So like these big impact crater basins or low elevations here in the north. So where this arrow is pointing is Jezero Crater, and that's where the rover landed. This is what it looks like zoomed out from orbit here. So it's a crater that was formed by a meteorite impact, like the one that wiped out the dinosaurs on Earth, but smaller. And here we can see an ancient river channel that used to flow into this crater here billions of years ago from the west, and another river channel that used to flow into it from the north. And here in the east, we see a river channel that used to flow out of this crater. And from the fact that there's channels flowing in as well as out and the elevation of the crater, we can tell that this crater used to host a lake. So billions of years ago, there was a lake environment of water filling up this area in Jezero. If we zoom in on this area here near where the rover landed, you see, so this is we colorized, just drew over the surface here to highlight important features. This is the ancient river channel coming in, and it deposited a delta in the lake. So this is similar to the delta at the end of the Nile River, which I'm showing here on the right. So here you see in the Nile River, this river channel starting in the Ethiopian highlands and coming down to deposit this delta, this triangle-shaped thing in the Mediterranean Sea. So that's similar to what happened on Mars billions of years ago here in Jezero Crater, with the river channel flowing in, hitting that standing body of water. On Mars, it was a lake, and depositing this delta. And that's really exciting because it gives us this conceptualization that this is an artist's conception of what Jezero Crater might have looked like in the ancient past, which would obviously be very exciting because these types of lake environments are habitable for life. And river deltas on Earth are habitable environments that are also very good at preserving fossils. So here's a picture that was taken when the rover first landed of the delta in Jezero Crater. And so now we have a journey to go to this delta and look at it more closely and see if there are any biosignatures or signs of fossils in that delta itself. And this would be really the most exciting thing we could find just with the rover. So these are what are called stromatolites on Earth. These are billion-year-old rocks in Western Australia that we know were formed by biology on ancient Earth. So if we could see something like this with the rover in this lake on Mars, that would be good, strong evidence that life once inhabited that lake. And that would be the first strong evidence of alien life, albeit fossilized and not currently existing today, that humans have ever found. But it's hard to just look at these things with the rover and definitively conclude that there are biosignatures, even if we see something as amazing as this. And so what's required is collection of the samples with the drill that's hosted on the rover here in this graphic so that they can be returned to Earth. So here's a picture of that drill that collects the samples. So these two parts of it here mount on the rock, and the drill comes in and drills into the rock. And those samples, here's a picture of that drill actually on the rover where we were testing out the arm movement. Eventually, we'll be able to engage that drill and drill into the rocks to collect about 38 samples. And eventually, those samples will get returned to Earth, hopefully in the 2030s. So here's a conceptualization of how that mission will work, where Mars 2020 comes in with this drill, collects samples of the rocks, caches them on the ground of Mars. Another spacecraft will come in, land on the surface of Mars, and this is joint sponsored by NASA and the European Space Agency. There will be a smaller rover that comes out of that lander, picks up all the samples, and then puts them back into a smaller rocket that will contain the samples, launch off the surface of Mars, and come back to Earth. So that will really be the way that we can strongly determine whether or not there are signs of fossils in this environment, is by getting the samples back to Earth. And Mars 2020 is the first key step in that whole process. And now we're doing things like driving around. Here's a video of what we call the wheel wiggle. So testing to make sure the wheels work. We know they work well now because we've done a lot of driving since, like this. Here's a bunch of images stitched together of the rover driving around, making wheel tracks on Mars out of nothing. And we're soon going to be doing this Ingenuity helicopter technology demonstration, the first time anything has ever flown on Mars. So this helicopter was stashed up right there in the belly of the rover as it flew to Mars and landed. And it's since been dropped from the belly of the rover to be present there on the surface of Mars, and will eventually take flight. This thing has a small piece of cloth from the Wright brothers' original airplane stitched onto it, such that we can take that piece of aviation history on Earth in this momentous occasion of aviation history on Mars. And here's a selfie of the rover here, which is really beautiful. You can see these images all over the news if you want to see more. Okay, now let's talk about the possibility of future human inhabitation of Mars. And this is a very exciting time for all of us to be alive, especially you younger ones, because you can really have an opportunity to participate fully in this whole process. So it's similar to voyagers traveling between islands in the Pacific on large vessels. Eventually, large vessels will take humans from Earth to Mars. And once humans get there, there will be some things that are similar and some things that are different. For instance, sunsets. Here's a picture of a sunset that I took from the top of Mauna Loa, looking out over towards Mauna Kea. And you can see, as you're all familiar with, the sky on Earth is blue and the sunsets are red. On Mars, it's the opposite. There's still sunset and sunrise, but the sky is red and the sunset and sunrise are blue because of that different composition of the atmosphere. The horizon on Mars is also much closer than it is on Earth because the planet is smaller. So the curvature of its surface is higher. It's more curved. So that horizon is closer and the sunset is going to be blue. But still, there are similarities in that there still is a sunset and still is a sunrise. There's also dust everywhere on Mars. Here's a picture of one of the veteran NASA Mars rovers, Curiosity in Gale Crater. And it's been on the surface of Mars since a few months after I graduated high school in 2012. And since then has accumulated a lot of dust. So this is something that future human inhabitants of Mars will need to learn how to deal with, because that dust gets in everywhere, just like the sand gets all in your beach towels when you take it back home and can get sand all over your floor that you need to sweep up. This dust could cause similar problems, but kind of on a much larger scale on Mars. Another thing that humans need to tackle to try and inhabit Mars is ways of finding water. We all know that water is essential for life, right? We got to drink it. On Mars, we can also use it since it's H2O, there's oxygen in it. We can use it to make air for humans to breathe, and also use it to make rocket fuel by combining it with the CO2 in the atmosphere to create rocket fuel that will allow rockets that land on the surface of Mars and have used up all their fuel to get there to then be refueled by the Mars atmosphere and water through some processing to then launch back and travel back to Earth so that we can continue to have this interconnection between the two planets once humans are there. And, you know, this is CGI. So the picture of Mars is real, but the humans are CGI'd on here. This is a very possible reality for the people of your generation, to have humans permanently living on Mars and living on the moon and creating a solar system where it's no longer just humans on Earth, but it's a dynamic environment of interplanetary exchange where we can find resources on asteroids that don't have any life on them and collect them to be brought back to Earth so that we don't have to extract those resources from Earth itself, which is a very special planet because of all the biology on it. And so you're really in a good position based on when you were born to participate in this whole process of exploring space, inhabiting space, finding resources in space, and honorably fostering our home planet, Earth, that is our responsibility to take care of as humans now as we travel out into the solar system. All right, so how did I get lucky enough to work on all this? I ask myself that every day. I grew up as a normal kid in Hawaii and had quite a fun journey to get where I am that, you know, some of you could take similar journeys or different journeys to end up in similar different places that would also greatly help humanity and help you find fulfillment. You know, I grew up going to the beach, going up Mauka into the forest, and enjoying the Hawaii lifestyle here. Here's me in a Honu. As I got older, around like late middle school, early high school phase, I was into exploring the ocean, playing drums a little bit, growing out the hair, you know. And it wasn't really until I was this age, about 15, that I got super excited about the subjects I was studying in school. It was some combination of the subjects becoming more advanced and more exciting, and also just the thought of what could be done with them later on as I progressed through my career and life. I graduated from high school from Parker School in Waimea in 2012. So here's me with all my wonderful classmates here. And then from there, went to Wesleyan University in Connecticut, where I graduated in 2016 after double majoring in physics and astronomy. From Wesleyan, where I had a great experience, I was able to go to grad school at Brown University, which I just finished in September of last year. Got to do a lot of great research on Mars and Earth, on computers, looking at images and data from Mars, in the lab where I was able to do some experiments to help us learn more about the ways that we evaluate what's on the surface of Mars. And I also had to have some awesome adventures to do field work, like going to Nanyuki, Kenya, with all this cool equipment to study that area there. And I also had the fortune of going into a 1.5 miles underground on Earth into Kid Creek Mine in order to sample the most ancient groundwater humans have discovered to date. So this groundwater is billions of years old, and it's been isolated from the surface for that period of time. So we were able to go down there and sample that stuff. This is really quite an adventure because, I mean, this place is in Northern Ontario in Canada, and we went in February. So this thing was, it was like colder than negative 20 degrees Fahrenheit at the surface, just snowing all over the place. Me, Hawaii boy, had to drive 8 hours in these like crazy winter conditions to get to this field site. But then when you get down into the mine itself, all the heat from the machines in the mine, as well as the geothermal heat flux from the earth itself, warms things up. So it was in the 70s of degrees Fahrenheit down there while we were doing this field work. That's enabling us to do research that I'm still working on with my colleagues who I went down into this mine with back then. And then that all took me to graduating from Brown and being able to work at JPL, which is what I'm doing now, working on the Rover. I feel so lucky to be able to do this. And, you know, I've given you kind of an outline of the path I've taken, but the path that you will all take is your own path. And there's lots of different ways and lots of different things you can do to contribute to humanity and help making the world and the solar system a better place in whatever it is you decide to do, whether it's by being an artist or by being a policymaker, whether it's by being a musician or a doctor, someone who practices culinary arts, education, social work, anything that you decide to do, you can do in a way that helps make the world a better place for all the humans who live on it, to help responsibly cultivate our home planet and help humans expand to the stars and do so in an honorable way where we're really taking care of our home and the places we will call home later on in life. Whatever your trajectory is, you can still get to some pretty amazing places. So, you know, in grad school and at JPL, I work with some people who went straight out of high school to Ivy League schools. I work with some people who graduated high school, took a couple of years off, went to state school, and then entered the workforce or went and got their advanced degrees. I work with some people who graduated high school, eventually went to community college and transferred to a 4-year institute, and then entered the workforce or went and got advanced degrees and entered the workforce. And we're all working together, shoulder to shoulder, solving and tackling these complex problems of space exploration. And no one is thinking about where it was you went to college or what you did and how you got here. What there is a mutual respect between all of us that whatever the circumstances were that you came from and whatever the path is that you took to get to where you are, you've gotten to this place through hard work and dedication. So whatever your path is, believe in yourself that you can achieve that goal that you would like to achieve, because you really can. And just don't listen when people unequivocally doubt you. Seek out mentors who will help you get there, and then figure out what it is that you love to do and pursue that full throttle. And even if it's not something you decide to do via work, if it's something you decide to do just as being a good member of your community, spreading aloha in your community, that is a positive way to contribute to the world too. And, you know, I'm excited to work with you all in the future on this stuff and to be part of a shared community that we call Planet Earth. And that's it. Thank you. Thank you for listening. And I'll just leave this up here while I take some questions. Thank you.
Okay, thank you, Jessie. That was absolutely fascinating. We all really enjoyed that. Now we have a lot of questions, as you can well imagine. So hopefully we'll get to as many as we can. And the first one is from a 5th grader. How will Perseverance handle Mars storms if they come to the rover's area?
That's a great question. So there are storms on Mars. They aren't like rain and thunder and lightning. They're dust storms. So some of you might have seen the movie The Martian. They have a dust storm there. The dust storms on Mars, while the entire planet is engulfed in dust, so it's very hard to see, because the atmosphere is so thin, the wind actually isn't strong enough to blow anything over. Like it can't blow the rover over. It can't really damage the rover other than by getting dust everywhere. And since this rover has an internal nuclear power source rather than solar panels, we don't really need to worry about the solar panels getting covered either. It's more like the lenses on the rover we need to worry about. But other Mars rovers have experienced dust storms, and you kind of put them into hibernation mode and let them wait it out unless it's determined that if they have a nuclear power source, they can continue working even during that time, which Curiosity did for a little bit in the most recent dust storm a couple of years ago, I believe. So it is an issue to address, but we got some experience and got it handled at this point. Good question.
Okay, next we have from Matt. Why do you call Ingenuity a helicopter instead of a drone?
Oh, that's a good question. You could call it a drone, and people do call it a drone. I just call it a helicopter because it uses that same technology to fly it around. So, you know, it's sort of like how you call a kayak a boat, but not all boats are kayaks. It's like Ingenuity is both a drone and a helicopter, but you could definitely call it a drone, Matt. Thanks for the question. It's good.
Okay, the next one is from Peter. Did the team have a working prototype of the Sky Crane system, and how did they do reliable testing in Earth's gravity?
Yeah, that's an excellent question. So we really, you can't do a lot of the reliable testing in Earth's gravity. A lot of it has to come down to just having engineered it very well. You can test the parachute in this big parachute testing range that's at a NASA center. So the parachute can get tested to make sure that's working well. But Sky Crane itself is much harder to test in Earth's gravity. And the entrance into the atmosphere too with the heat shield is harder to test in Earth's thick atmosphere. So a lot of it just comes down to needing to have engineered the thing really well, done every single test the engineers possibly can to make them as confident as possible. And then, you know, sitting back and hoping that it works once the thing is already flying to Mars and about to land there. So that's about how it works. And it's amazing. This Sky Crane technology was also used to land the Curiosity rover back in 2012, but they didn't have those video cameras strapped onto it to take the videos that I showed you today from the NASA YouTube channel. And so even the people who had built the system that had successfully landed something at Mars had never seen it in action until they tried to do it this time. So it's a complex problem and really a testament to how teamwork and great engineers can make amazing things happen.
Next question is from Kristen. Since Mars has rust on its surface, if you got scratched, would you get an infection?
Oh, that's a good question. Well, so I think that, you know, I'm not a biologist or a medical doctor, but my understanding is that if you get cut by rust, it's more the bacteria that are the issue than the rust itself. And because that rusty iron oxide red material on Mars is so cold and dry that there's no way anything could live there, I don't think it would be a problem. It could be a problem if you were outside and your spacesuit or your pressure suit also got cut, because then you need to cover up that seal and get back inside so you can stitch it up.
Okay, the next question. Can you explain how Mars time works? How do you tell time on Mars?
That's a great question. So yeah, on Mars, we don't have, you know, clock towers or a cell phone or satellites to tell you what time it is. So the way it's done is mostly just based on Earth time. So we know what time it is on Earth, and then, you know, we just use Earth time to translate to Mars, but we know what the position of the sun is just by knowing the orbital period of Mars really well. And there's also a calibration target on the back of the rover that can be used as sort of a sundial just by the shadow of this kind of column that's sticking up and where it's cast on this round object. But days on Mars are about 40 minutes longer than days on Earth, a little bit less than that. So during this first 100 days of the mission, the rover team has been living on Mars time. And so that's Mars time local to where the rover is, because just like, you know, in Hawaii right now, it's 6 hours earlier than where I am on the East Coast in Providence. So the sun will set here earlier. It's the same on Mars. The different parts of the planet are illuminated at different times. So the rover team during this first 100 days of the mission is living on Mars time at Jezero Crater. And the reason that we do that is so that we can collect pictures and data when the sun's up, that a lot of that's harder to do at night. But it also means that because the days on Mars are 40 minutes longer, our work days shift to be 40 minutes later every day. So sometimes we're up working in the middle of the night to get the rover plan made for the next day. And then sometimes it's totally normal hours. It really just drifts.
Okay, we have a question from a fifth grader. What materials did NASA use to make Perseverance?
Oh, that's a great question. So there's a lot of materials, more than I could possibly list off, at one time. The rover itself, the body of it is made out of different kinds of materials that are both lightweight and strong. There's lenses on it that are made out of a variety of materials that are both robust to kind of the dust, but also that you can see through. The electronics inside it can be made of similar stuff as your computer, but with kind of the space flight hardware qualified quality to its making. And yeah, it is a very, very complex machine. So sort of like how in your car or your parents' car, there's a lot of different materials that go into that, different materials in the engine, from plastics to metals, to different materials in the wheels, to different materials in the electronics. It's like that, but even more complicated because of all the instruments on board. So that's a great question, and one that I probably didn't even answer thoroughly enough to meet your satisfaction. So great questions, and I would follow that up and look it up, because I'm sure you can find a list of some of the thousands of things that are publicly available to see what the rover is made out of. Thanks.
Okay, we have time for 2 more questions. And from Paul, is a more permanent human presence on Mars a priority over the moon because of the potential of having water there?
Yeah, that's a good question. So I think that both are necessary both are smart things to do. So on the moon, it's obviously easier to make a permanent human settlement there because it's closer, and it's easier to resupply that settlement from Earth. And there's some ice on the moon that you could get resources out of, but I think it would be much harder to have a sort of self-sustaining presence on the moon compared to Mars. But by going to the moon, like through NASA's Artemis program, you're able to start encountering a lot of the problems that you'll see on Mars. Like, for example, fine-grained dust. The Apollo astronauts, when they walked out on the surface of the moon and then got back into their space capsule, they were covered in dust, and some of that fine-grained dust had even gotten inside of their spacesuits. And the dust on Mars is also very fine-grained and can kind of get into everything. So to figure out how to make your systems robust to all that dust, that's something that we can kind of learn on the moon in that more controlled environment, where if something goes wrong, Earth is only a few days away, as opposed to learning it first on Mars, and you're sort of isolated and out there, and Earth can't really help you very much. That's sort of the way that studying the moon and having human inhabitation there at the same time, maybe a little earlier on the moon and then progressing to Mars, can help us do the Mars human inhabitation in a safer way. Good
All right,
question.
The last question. How can people stay up to date on this mission?
Yeah, great question. So you can subscribe to, there are all sorts of email servers that NASA has, both Mars specific and just NASA specific. So if you go on to NASA's website, you can sign up for one of those emails, or just check NASA's website regularly, and they'll give all the updates. Like when the helicopter flies, they'll give an update about that, and you'll be able to see it, as the people who write the news are seeing it. You can check out NASA Live TV to see updates on the mission there and press conferences. So go to NASA's websites. They do a good job of telling you the information as it comes in, and just check it out day to day and see what's happening. And as you check out what's happening with the rover, you'll also be able to see all the other amazing things that NASA is working on, which have to do with Earth, have to do with Mars, have to do with the outer solar system, the asteroid belt, and maybe can engage in some of those cool things as well.
Great. Well, mahalo, Jessie, for this great presentation. And I want to thank everybody joining us today. Let you know the recording will be made available in a couple of days on our library website, librarieshawaii.org. And just a plug-in for Astro Day is being held in Hilo at the Prince Kuhio Mall from April 1st to May 2nd. April 30th to May 2nd. So please join us. Thanks again so much, Jessie.
All right, thank you. And mahalo everyone for coming. Have a good rest of your day. Aloha.
Aloha.